Okay, so I mean, I have different options for today, so maybe let's do something that probably would be helpful for you for the exam, which would be to do like another example. All right, this time maybe a little bit more complicated or not as straightforward. So let's just do another example over here. Let's see that a little bit. Okay. Let's see if that's better. Oops. So example. I got a red. We'll work it out. So for this case, we need to find the equation of motion for the following system. So there is okay, so this is a pulley that has like, if you want two pulleys welded together, no? So if you want, you can have on this side let's see how can I do this. A string is going to come in here. Okay, I don't know how this is possible, but this is the example that I have. If that we can change it, it will be a spring K over here. And then on the outside here, there's a damper C. And all this is attached here to the cylinder. Okay, and the first one has a radius R. And this one here is 2R. Okay, we know that the radius is 0.8 meters and is equal to 20 kilograms. Moment of inertia of the pulley would be mr squared over 2. The constant of the spring K is 60 Newton meters. And let's say that C is equal to 24 Newtons second square divided by meter. Okay. So then we're going to define some initial conditions. That would be that at x equals 0, this is 0, and that the velocity at time t equals 0 is 0. So what we need to do is, what we need to do in this problem is to determine the equation of motion and then solve it, okay? With a MATLAB, just plot it. Okay, so here is like I say all the time. Okay, what is the best thing is to just go and start the procedure, no? Okay. So first, maybe what should help you a little bit. What type of motion is this system going to have? What are the type of motions that exist? Translation and rotation. So which ones is this one going to have? Is it going to have rotation? Okay. Is it going to have translation? Ready? So if this is weight, this could not be bouncing up and down and then rotating this way.
Is the ball itself mass?
Yeah, of course.
Okay.
I mean, so this can be moving in translation and rotation, no? Do you have a question about this, or is it clear? This system can be moving up and down if it was straight, but also be rotating, no? Okay, so this should help you. So that will mean that, and I rather use the Newton's approach instead of the Lagrange. But if you want, then, I mean, you can do it or we can do Lagrange, okay? But you can go and check. So first step would be what? What is the first step? some type of free body diagram. Really is not free because it's in motion. Free means static, but who cares? Some type of figure, no? Okay, that's what's important. So you need to do one, remember, for the left-hand side of the Newton's equation. So we're gonna do again one of the double pulley here. And this should be equal again to something like this. Okay, now, what would be the forces being applied over here? Okay, so will be force of the spring applying here at, correct, let's say this will be Kx. What else? Force of the damper here, that one should be equal to what? Cx dot. And what else? The weight. Okay, we have one more. What should be the extra one? What happened here? And tension. Okay, and since we mentioned x, we start from where? We look at the motion of x, you want to do it going up or down, x. Let's just do the normal sign convention, okay, up, no? You want to call this, okay, let's call this x because this is going to be moving in one direction. We could call it y, but just call this x. Okay, next, what type of motion is this going to have? This we're going to have here what? MA or MX double dot. All right, or what is the type of motion we can have? Let's say this is point O, I sub O alpha, which would be I sub O theta double dot. All right, any questions so far? Because to me, I think this is the most difficult part.
Do you choose when you have the final equation, you choose whether it's going to be x or in terms of x or in terms of...
That's what we're going to have to decide next, okay? So since you mentioned that, let's say we're going to write the equation of motion. We can decide if then x or theta. You want to do x or theta? Okay, so let's say let's keep in function of x, okay? That way we can think about it. But that's a very good question because you have the choice, no? Do you understand what he's saying? Yeah, okay. All right, so here we go. So now step 2 is what? Kinetic equations, but basically would be Newton's equations, no? Because there is translation, we need to apply summation of forces equals to MA, and because there is rotation, we need to apply summation of moments equals to alpha. So let's start by summation of forces equals to MA. In this case, we only need to apply it in one direction, no? Only on the x direction. Maybe let me put it here, x direction. So what will be the equation? Okay, this is the most difficult part, I think, the figure. Once you have the figure, it should be straightforward. So it would be T plus Kx plus Cx dot minus Mg oh, we need to here to be careful with something. Hold on one second. Yeah, we have to be careful here. Okay, can we call this one? Sorry, guys. Can you call this one x sub k and this one x sub c dot? Because let me just do notation now. We talk about it, okay? K and c. Let me finish to write down the equation and then we can talk about it. And this should be equal to X double dot. Okay, next we're going to do summation of moments about point O equal to I sub O alpha. Before I move to this one, what did I change here? The X sub, put here X sub K and here X sub C. And here the X, this is the motion of the point O, no? Of the CG. So you agree that when this one, if this was only moving in translation, when this is moving, let's say 1 unit up, this one will be moving 1 unit up, and this one will be moving 1 unit up, no? Okay, but what happens if this is rotating? Let's say it rotates counterclockwise. So it's going to be motion due to the translation plus an extra term due to the rotation, no? So you can say that X sub naught is not going to be the same as the X of this point, no? Yes? And the same thing over here, no?
So it's rotating up and rotating.
Correct, yeah.
Doesn't have to rotate.
I mean, but you have the choice. So you need, I mean, you can have that motion, so you need to take that into consideration, no? Okay, so that's why I changed it a bit, and yeah, and we can look at it, okay? Okay, so I'll do that next. So summation of moments about alpha here, what we're gonna have? T times R, no? So it will be counterclockwise, this will be going clockwise, so it should be negative. Then plus K X sub K times R plus C X damper sub C times 2R. 1, 2, 3, 4, 1, 2, 3, yeah, 1, 2, 3, 1, 2, 3. Sorry. And this should be equal to I sub naught alpha. What happened? Okay, so it will be our equation 1. Our equation 2. Okay, so now let's say we have this. And here I'm just going to put some simple equations where in these ones we know very easy that I sub naught would be equal to m r square over 2, but I might leave it under r sub naught. And alpha we know will be equal to theta over that. Okay, if we wanted to write that. So obviously here we have two equations. How many unknowns we have? We have T, we have X sub K, X sub C, 1, 2, 3, and alpha 4. We have like 3 unknowns, no? So we need to find additional equations. We have T, 2, 3. Yeah, because I already put that one. Okay. All right, so step 2. So let's see if we can find a relation. So let's see. Step 3. will be additional equations. So let me just redo again here the figure. Okay, so this will be kind of a review if you want from dynamics. Not redoing the whole thing. Yeah, I might redo the whole thing if you want. Just do this one. So in this case, let's see, before I tell you the answer, maybe you know. What is this point over here called in dynamics? When did you take dynamics?
Years ago.
Really, got far away? Okay, so basically, do you remember something called, like if you have something rolling, remember something rolling on the surface? It was something called the center center.
Oh, yeah.
So if you have to think about this pulley, if you want, like if it was rolling, it would look like it would be rolling from this point, no? Yeah? Okay. So what is specific about the instantaneous center is that if you take a picture right at that instant, it would look like this pulley is rolling about this. So the velocity of this point here is 0, no? So I'm going to do it quick, okay? So I think this is probably the fastest way to do it. So what was the distance of this? Let's look at this one. We have the T. We have this one here. Let's see, this one here, maybe I did this wrong. This one here, plus this one here, let's see. Let's not do those lines, okay? Let's see what this will give us. Okay, so let's call this point here point O. Okay, so I was trying to simplify it, but might not be a good idea. Okay, so let's call this point here P. What will be the velocity of O of the center from point P? We know the velocity of P is 0, no? It's in a center. So this would be equal to VP. I mean, this is, didn't want to do it this way, but I think it's probably the fastest way. This one I call this R of O with respect to P. VP is 0. I might give too many details for this one, but it's not going to hurt. So this would be IJK 0 omega. That way there will be review of dynamics. What is the position of O with respect to P? I mean, you can put positive, negative, doesn't matter. Let's say negative 2 R's. But what's important here is that this is going to give you that the O will be equal to what? 0 minus 2 R omega. Okay, so this will be, this motion here will be related to the motion of X, correct? Yeah. Now, let's call this point here, whatever, let's say this one A, okay? Where the spring is. Is that what the spring is? Yes. So what would be VA? We can do it again from point P, will be VA plus omega cross R of A with respect to P. I mean, let's do it one more time. This will give us here IJK 0 omega. Now, what is the distance between P and A? would be 3R, no, or negative 3R, it doesn't matter really, positive or negative, would be VA, would be given then to 0 and minus 3 omega. And this will give you the X of the, how do we call that one? X of K, will be related to X of K. Okay, let's go now the last one when the damper is point B. We're gonna have VB equal to VP plus omega cross R of B with respect to P. And this will give you IJK of, let's see what, 0, 0 omega. And what will be the distance over here would be 4R, no? And this one is the one that will be related to X sub C. Okay, so now knowing that velocity is displacement over time. So basically for the same amount of time, what will be the ratio between those two displacements? So let's say we divide everything by 2, no? Yeah, so let's say when this is X, instead of 2X, XK will be moving how many times X? I mean, you can divide everything by 2, no? So one should be moving what? 3.5 X, no? Because omega R is the same thing, no? And X sub C will be what? Which will be 2X, no? Correct? You understand what I've done over here? Okay, okay. So let's go step by step. So let's say here, let's call these equations here, whatever, equations letter A. And let's say substituting equations letter A into equations 1 and 2. So let's see, what was equation 1? So equation 1 was T plus K X sub K plus C X dot sub C minus mg equal to mx double dot. So this equation will become what? T plus K times what? Three half of X, no? Plus C times 2x dot, let's not forget the dot, minus mg equal to mx double dot. Okay, so this will give you what? T plus 3 half kx plus 2cx dot minus mg equal to mx double dot. Sorry for that. Can I zoom out a little bit? Oh yeah, good. So this will be the new form of equation 1, no? So this is still equation 1, no? Roman 1. Now, if I do the same thing for the second equation, maybe let me go to the next page. Okay. So if I go to the next page, equation 2. Let's see, what was equation 2? We need to go back to this equation here. So it should be this one here, minus t times r plus k x sub k times r plus c x dot c times 2r equal to I sub naught. Let's replace this one, but already theta sub a dot. So we follow exactly the same approach. This is going to give us what? Minus t times r plus k times x sub k is what? 3.5 x times r plus c x sub dot is what? 2 x dot times 2r will be equal to I sub naught theta double dot. This will give you minus t times r plus 3 half kxr plus 4c x dot r equal to r sub naught theta double dot. Let me just rewrite this by convenience. I'm just going to rewrite this one as I'm going to divide everything by r. Okay, so I will give you minus t plus 3 half of k x plus 4c x dot will be equal to I sub naught over r theta double dot. Okay, this will be our equation 2. Oh, guys, hold on 1 second. Let me look at something. Oh, no, perfect. I think we're good. Okay. Oh, no. I don't know what to do here. You see battery bar diagram? I changed the problem. So you see what I did this one here? I put it right here, no?
Right.
And here I put it here. So, okay, what can we do? So can we just move this one over here now? We'll have to do a modification. Sorry for that. Do you see how is that going to change? You see why the feedback diagrams are important, no? So sorry for that. Let's move this one here. So this will be our point P here, will be here now. So let's see how is that going to change everything. It would change everything by a factor of whatever it is, 1, no? Yeah, so basically this one, instead of being 2 R's, will be R. So, but it's going to change all the equations. That's what I want to say.
Yeah.
So sorry for that. It will be minus R omega. But do you see the mistake that I've done? Sometimes it's good to do mistakes because I think live you learn a lot more from your mistakes than what you do right, no?
Right.
Okay, so I mean, I'm not trying to justify, no? But anyway, so now if we go from point A from point P, which would be instead of being 2, instead of being 3 R's will be 2, no? So this will be 2 and here will be 2. Okay. And then when we go from B to P, instead of being 4, basically we're just removing 1 R, no? It would be 3 R's. And 3 R. But basically now what are we going to have? Instead of 1, 3.5, 2, we're going to have 1. This will be 2, no? And this will be 3, no? Yes? So, all right, bad luck. We have to change everything. So this should be here instead of 1/2. This should be 2, no? Correct. So this should be over here 2. And this should be instead of 2, this should be a 3. So this one becomes a 3. So I'm just going to write the equations here before we do any mistakes. So if I rewrite this equation here, okay, let's do that at the end. So any question about this one? Do you see the mistake that I have done? If you want, you can blame me, okay? It is what it is, all right? Now for this one, we do the same thing. So we need to be careful. X sub k, now this is 2. Instead of 2/3, instead of 1.5, so 2. And this one is 3, no? 3. So this is going to give us 2 over here and 6 over here, correct. So again, this will be a 2. And this becomes a 6. Okay, so since we are here and we did on this mess up, let's just do a quick summary. We have T. Oh, it's going to work out good, this. Now that I just do this. Plus 2kx plus 3x dot minus mg equal to mx of a dot. And the one is minus t plus 2kx, is that the same? Looks like. Plus c cx dot equal to I sub naught over R theta double dot. Okay, it's good that I did this summary because now I see exactly what I need to do. So basically in this equation, we need to write down the equation of motion, so this thing aloud, in function of, before we do that, so we follow the procedure. What is the other variable now that we need to change? Is this one over here, no? Okay, so theta double dot is alpha How can we relate this? Okay, let's go back to this equation here. All right, let's go back to this figure here for the additional equation. All right, so let's see the acceleration of point O from point P. So if you remember from kinematics, this will be the expression with respect to P. Okay? I don't know how much you remember, but let's say system is initially at rest, or these two terms cancel each other. So really here we have left ijk of 0, 0, alpha. And what is the position of O with respect to P? Is just 1R, no? Okay, if you don't know, stop me, okay? So will be position of O with respect to P is R 0, 0. Okay, so if you look at this equation, this is going to give us that A sub naught will be equal to R alpha or this will be equal to R theta double dot. And by definition, what is A sub naught? Is the second derivative of x over dt squared. So basically this gives us the relation x double dot equal to R theta double dot, which is going to mean that theta double dot will be equal to what? X double dot over R, no? I cannot make it everything long, but okay, so what I'm going to do now is substitute this one into this equation here, no? Okay, so substituting C into 2, this will give us what? Minus T plus 2kx plus 6cx dot equal to I sub naught over R squared x double dot. Okay, so I know we did a lot of additional equations. This probably will be more complicated than what you have been doing. But what should be the last step? We did step 1, free body diagram. No, 2, apply kinetics equation. 3, additional equations. 4, we can go and solve. Okay, so once again, I'm going to write the 2 equations. I wanted to do it here, but I waited in order to follow exactly the procedure. So here we go. Let me just rewrite the two equations now. So we have the equation solved. We have the first equation, which is, let's see, which is what here, t plus 2kx plus 3cx dot minus mg equal to mx double dot. So equation 1. And the one is minus t plus 2kx plus 6cx dot equal I sub naught over r x double dot. And this is our equation 2. Okay. So here, almost the solution is here. If you want to kind of put it here. Okay, we need to write down everything in function of x, no? Or x double dot. So what is the only variable here that we need to eliminate? T. Okay, so here's very simple. What can we do in order to eliminate t? We can either solve for t here and substitute over here, but since in so friendly form, what can we do here? We can just add these two equations, no? Correct? So let's see. So this then will cancel with this t, and we have what? 4kx plus 9cx dot minus mg will be equal to m plus I sub naught over r x double dot. Okay, or really, if you wanted to write on the general form, this would be equal to m plus I sub naught over r square x double dot plus 9c x dot plus 4kx equal mg. Yes.
Is the R on the line before that's supposed to square as well?
Yes. So I forgot to put the square. Yes. So square here and square over here. Thank you. Okay, so if you ask me, this is the general form of the equation of motion, but since in this class we have only solved, to know that the right-hand side is equal to 0, what do we need to do in order to make the right-hand side equal to 0? We need to do a change of variable, no? Which basically physically will represent what? That we write this equation from the equilibrium equation. So we first need to find what should be the deformation of this when you just leave it hanging, no? You do this weight. But before we do that, let's look at this equation. Do you remember what we said before? Is that it should be one term of the acceleration that is due to translation and one due to rotation, no? Or the deformation. So this m over here takes into consideration what type of motion? This would be the translation, no? Mx over there. And this term takes into consideration the rotation. So you see it here in the two terms, no? Okay, we could have combined, but So let's call you this equation star if you want, all right, or whatever you want to call it. Okay. So let's over here the above equation is non-homogeneous. Meaning right hand side not equal to 0, comma, and in order to make it homogeneous, a change in variable, so let's say from static position, is necessary. So in other words, I remember how we did it, but we find out now with the math. We said that the position x is equal to x bar plus x equilibrium. Okay, which this means that okay, we can leave it this way, sorry, just leave it that way. It's fine. Okay, where x eq corresponds to equilibrium position. So what happened at equilibrium position? There is no motion, no? So acceleration is 0 and velocity will be 0 as well. Okay, so if you look at the equation, then this will give us what? This is 0, this is 0, this will give us what? 4kx equal to mg, so this will be m equilibrium, x equilibrium, which means that x equilibrium will be equal to what? Mg over 4k. All right. And x equal x dot plus x equilibrium becomes what? X equal to x bar plus mg over 4k. Almost there, huh? It's taken us a while. I thought it was maybe a bit faster. So now, finally, what can we do? Substitute this one, d, into the equation of motion, no? So substituting d into the equation star, I should have put just star. What do we get? m plus I sub naught over r square. Okay, that's where we start the funny notation. So this is a constant, no? So if you take the derivative of a constant, you get 0, no? So this should be equal to what line? X bar double dot, no? If you take the second derivative of this one, you get x, this one will be 0, x bar double dot. Yes, everybody? Okay. Now you do the same thing for the second one. We get plus 9 c x bar naught for the same reason, because the first derivative of the constant will be 0. Then the last one will be plus 4k times the x bar plus mg over 4k should be equal to mg. So what's going to happen here? You see these terms here is going to cancel this one, no? So at the end, we're going to have, oh, you don't see over here, that. So we're going to have that. Our equation of motion is m plus I sub naught r square over x square over r square times x bar double dot plus 9c x bar dot plus 4k x bar equal to 0. What? Yes, the mg cancels. That's why you end up with 0 over here. So now this equation here is homogeneous, no? Okay, we need to do a little bit more algebra for a second. That will be it. We are doing all this stuff because we say that all the equations end up being of the same form, no? But what is the same form? X double dot plus omega n x, no? Plus cx equal to 0, and then we could solve, okay? So that's basically what we're going to be doing. You don't have to do it, but, okay. Personally, I think we could leave it this way. Can we leave it this way? Okay, I'm just going to add one more thing in the middle, because I think that's the way sometimes they ask the questions in programs. If somebody asks you to find what is the natural frequency of this system over here, what should you do? Basically, the natural frequency is which one this one will be moving naturally forever, no? Okay. What do we need to do to this equation? What will be that term? Right, maybe I'm going to have to do what I didn't want it to do, but let's do it. Basically, I can just take this equation here, okay? Or I could rewrite it as what? X bar double dot plus 9c divided by m plus I sub naught over r square x bar dot plus 4k divided by m plus I sub naught over r square x bar equal to 0. So let's see, I mean, I did all this stuff different. We can solve this different, doesn't matter. Okay, so this would be x double dot plus 9c over m plus I sub naught squared plus, remember this term is equal to what? Omega n squared. No, this is the term of the natural frequency. So we can say here where omega n squared, where omega n will be equal to what? The square root of this one over here, what will be the natural frequency of the system. Okay? So sometimes the same thing, like instead of asking you to find the equation of motion, to find the natural frequency, you know? Basically, you need to go through the whole same process. All right, so we have this. Okay. So we found the solution, no? Okay. So if you want, let me just write it down. So I'm just going to rewrite the equation like we are over here. So all right, so we found the equation of motion. Now we have two ways to solve the equation of motion, no? Yeah? One will be to do it numerically, the one to be to do the analytical solution. All right, so I mean, since if we put the values, we can probably do it very quick, but I don't like to put values. Okay, I don't know how messy I'm going to end up doing this if I don't want to put values. So what should be this page? We have a lot more than 4 pages. 1, 2, 3. Okay. Analytical solution is obtained as follows. So let's see, what is the first step? First step to do analytical solution? No, what is the first step? How do we find that? Go back to your notes. What do we do? Wait, didn't start working on the assignment? I mean, no, that's not part of the assignment. So this will not be part of the exam, okay? The exam will be equivalent springs and find equational motions, not to solve them. So what is the first thing you need to do? Assume the solution, no? And we say you assume the solution, which is of the form of sine and cosine, so it's called assuming harmonic solution, which means in this case that x bar of t will be of which form? So let me call it constant. I don't want to call it c. I think we did that last time. What name can we give to the constant? A, B, C, D. Just a letter, okay? D exponential. I think we used last time we used C, no? And we have to move C to C bar. Remember? So if we do this, then what does that mean? You have x bar dot will be equal to what? Minus lambda d exponential of minus lambda t, and x bar double dot will be equal to what? Lambda squared d exponential of minus lambda t, no? What is step 2? Correct, so plug in or substitute. Into equation of motion. So, okay, you see that all of them have in common the d exponential minus lambda t, no? Go a little bit faster here because of the time. So the x double dot remains unchanged. This will be just lambda squared. And now the dot term will have minus 9c divided by m plus r sub naught over r squared lambda plus this one here that basically remain unchanged plus 4k over m plus r sub naught over r squared equal to 0. Okay. All right. So over here, now what do we say? I don't know if I did that on step 3 or step 2. Okay. So what do we saw here? Above solution, above equation is satisfied if only if what happens? Is 0. What is the name of that solution? Trivial solution. Or then what needs to happen? The term within brackets needs to be equal to 0, no? So 9 minus 9c over m plus I sub naught over r squared lambda plus 4k over m plus r sub naught over r squared equal to 0. Okay, and all this problem is what is called, I mean, this equation here is what is known as the, maybe you heard that one in vibration, characteristic equation. Characteristic. Does that round sounds familiar? Okay. So, okay, and this is a quadratic equation, no? So let's find. So that's why, you know, to start substituting values should be good. So, but solving the quadratic characteristic equation. I'm switching to software, okay? I'm not gonna do that by hand. So if you want, you can do it with me. That way you have your files, okay? I don't know if we use that next time or not. Last time, Daniel, use it. Did we use Maple last time? A little bit? Okay, so we use Maple here. So I'm probably gonna do with Maple, whatever is left over, okay, of the problem. And you can do it with me. So open Maple, please. And I probably need your help. What's wrong over here? What did I do over here? I don't know what happened here. I don't know. See. Oh, okay. Okay. Okay, I don't know what I'm doing. I think I hit something with my leg. So, new document. Okay, I'm gonna, might not be the more elegant way, but I like symbolic. If I would start putting values, would be very quick. But I think then to start is a bit harder. So let's see. Our characteristic equation, let's just say AQT is equal to what? Our characteristic equation is equal to lambda square minus 9 times C. Oops. 9 times C divided by M plus I. Gibson, I'm going to call this one divided by R squared. Don't call it just only I because you might think it's an imaginary number. Times lambda plus 4 times K divided by M plus I naught divided by R squared. Probably MATLAB would have been faster this time, but it's fine. Okay, so what do we need to do? Solve EQT for lambda. Okay, they don't look that simple, the equations, no? I don't know how to do this. I don't know if that will work or not. So it's over here. Lambda 1. There's multiple ways to solve this. Lambda 1, let's say, will be this root over here. And lambda 2 will be this one over here, no? Okay, I mean, we could use what we did the other day, but since we are doing it that way, the crazy way, we could put values if you want, then it will become a lot easier, okay? But then what would be the solution? What would be this step? Now we can substitute lambda 1, lambda 2, where? How can I click here outside of this? We can substitute, now we have lambda 1, lambda 2, we can go and substitute into the assumed solution, no? Which is this one, correct? Okay, so this will give us, you see, I'm showing you, I'm doing it with you live, okay? I'm not copying any solution or anything. So this will give you, let's say, solution X will be equal to what? Our variable D1 plus, times the exponential of minus lambda 1 times t plus d2 lambda 2t. Are you doing that in Maple or you're just looking at it? Okay, or MATLAB, or even better. If you are doing MATLAB, we would have been faster. Okay, what did I do here? Lambda, I forgot the d. Lambda. So, I mean, it's going to look ugly, no? It's not that horrible, no? Now, what do we need in order to find D1 and D2? We need to apply the two initial conditions, no? What were the initial condition is, so first initial condition is to say what, at t equals 0. So, yeah, so I don't know how we're going to do this, so can I do this? Okay, it's not going to work, okay. I don't know what to do here, so, all right, so let's say here, equation, initial condition 1. I don't know how to do this. Okay, I'm going to say at t equals 0. I mean, we know what this is going to be. At t equals 0, what is x? Not t plus 0, t equals 0. I'm not able to put the equal sign or what? Oh, no. Okay, what is that going to give us? One equation which is going to be d1 plus d2 equal to 0, no? Okay, so equation 1 here would be d1 plus d2. Is that okay? All right. Now, I probably need to restart over here. Here, maybe I could do this, create another one, and restart from 0. Otherwise, it's going to take 0. So 0. MATLAB would have been better, okay, for this. Oops. That's because I put the text order. So we have this. What is the second condition? We have it for the velocity, no? So we could take differentiation of x with respect to t. And this is going to give us something ugly. Okay? But whatever, we don't care because he's going to do for us. So in this problem, what do we solve? T equals 0, what is going to be equal to 0? The velocity, no? Okay, so this is very ugly. So the second initial condition will be, the second equation for the second initial condition will be this horrible stuff over here. But again, we let this solve it for us. Equation 2. All right. Finally, what do we need to do? Why do we use the boundary conditions? The initial conditions. I don't remember how to do this. I think it's this way. So EQT initial condition 1. I'm not sure if that's the way to do it or not. EQT initial condition 2. These two equations for D1. I didn't put an underscore. I'm rewriting these two equations.
Yeah, at the bottom, solve when you put in your second equation.
Oh, I didn't put. I see two. I mean, I don't know if this if it is this way, okay?
I thought you just solve it like you put each equation.
Maybe. I don't know. I'll do the truth. I don't know. I'm doing it with you lives. Obviously, it's not that way. Okay, so let me restart here from 0. Maybe. Zero. Is that possible? See here, I know it's not a good solution, but it looks very strange. It cannot be 0 because then it will give you everything will be 0, no? So let's see. Hold on 1 second. Look at this because I did it here in a different way. Okay. So it's overdamp. No, they're not 0, obviously. If I put values, we can start maybe, let's see, did I copy minus plus? I think here I didn't copy a minus. Looks like, no? So let's just copy everything again and see what happened. If that is really my mistake here. All right. Let's redefine this one here. Okay. What is wrong here? This, so as we say, this will be the solution for the X bar. So lambda 1, lambda 2 is for the X bar. Now here, this is the solution for X. So X is the solution for X bar. That would be this part plus the static solution. Okay. So it's this one over here. So you see, this will give us what? This would be the velocity. So I'm guessing this first equation here now is going to give us D1 plus D2 minus n times G divided by 4 times K. All right. Now this one, I think should really take that into consideration or not? Yeah. I think the second one stay unchanged because the derivative for that will be 0. And now we have this. Okay. So now D1 and D2 will be equal to this, which looks horrible. But what happened? Okay, now if you do this, and let's say you come over here and you start putting values, what were our values? We had, I have it right here in front of me. If we do R equal to 0.8, M equals to 20, I sub naught equal to M times R squared divided by 2. Then what do we have? K equal to 60 and C equals to 24. Should become a lot easier, no? G equals 9.81. Thank you. We can restart. There should be the two roots. This becomes a lot easier now. Okay. I think this should be unchanged. Yeah. Okay, so at the end, what are we gonna have here? And D1, D2. Okay, and finally, what is the solution then? I mean, I can rewrite it, but probably have it over here. This is X. The equation of motion becomes what? Oops, because we put it at t equal to 0. So maybe what I can do here is okay, let me eliminate here the t equal to 0. Just say, we don't need this one anymore. Can just put it this way, it should not put the value of X. Let's restart from 0. Come on. D2, and here we can put just this one. Now should work. This should be the final solution. Okay, doesn't look that pretty, no? Okay, I have no idea how to do this because I've never done it. I always do that in MATLAB, but I'm sure we can use plot for this one. Have you used plot in Maple? I never use it, so. Plot fx. Okay, doesn't look that bad. So plot x for t. I don't know if that's going to be the way to do it or not. I have no idea what I'm doing. Okay, but I'm got so lucky. Okay, so if you look at this, look like this is going to be overdone, no? Okay, but again, I mean, I know we don't have time, but another way to do it would have been to do what? If you do this symbolically, you can solve for this value over here, no? The value inside the parentheses, you find what is the critical damping, and then you can find what is the variable XC, and you can substitute into those equations that I gave you, no? Okay, but you don't have to do that, okay? I did it here because here I use the powerful of the computer, no? I mean, I wasn't expecting to spend the whole class, but basically that's what you can expect for the following assignment, no? Something like that. A couple of these problems. Yes?
We could have just used the skeleton of the MATLAB code in that last class.
Correct.
Do it small.
Correct, and that's what I wanted to do, to do it numerically. Yes, that's what, if we had time, that's what I wanted to do to solve this numerically. It will take us less than 3 minutes, okay? To find, you see, an ideal solution can be a little bit tedious, no? So were you able to take this or you want me to save this?
Can you see?
Okay, let me just save it what is this semester.